We will now continue with our user presentations, and I'm happy to hear now something about electroquasi-static modeling of biomedical simulation. So, thank you very much. Stimulation, sorry.
Yeah, thank you very much. Yeah, my colleague Vienna and I will present you a bit about what are we doing in Rostock on electrostatic modeling of biomedical stimulation. So, we are from the research center called ELAINE. So we are a consortium in Rostock and corporations in Germany focusing on stimulation with biomedical implant technology. So our focus is on the top left, the multi-scale modeling of active implants. So we stimulate different tissue types, cell, cartilage, and the brain for different application in the human. The basis for this, and I don't want to go into detail because probably most of you know about it, are Maxwell's equation. What in specific we use is by neglecting magnetic induction, assuming time-varying electric fields, so we get the EQS, the electroquasi-static approximation of Maxwell's equation, which is valid for our case because we have neglectable magnetic fields. And how this is used in the different applications, my colleague Vienne will first tell you about the cartilage case.
Yeah, so I would like to talk about the bone and the cartilage regeneration. So human cartilage is nearly incompatible of cell healing due to the lack of blood vessel. Therefore, the injuries tend to become worsened with time. That's why the heteroarthritis, which means the defect in the cartilage or the bone erosion, can lead to the long-term pain and disability. So as of 2021, around 600 million people are affected with OA, and it's projected to around 1 billion by 2050. And then, electrical stimulation have significant interest to enhance the healing and regeneration of bone and the cartilage. However, the biological mechanism between the electric field and the cells is not completely understood, and therefore the transition in clinical practice is not yet standard, and the conflict observation linked to the unknown local electric field and insufficient technical documentation. However, several studies show the positive effect of electrical stimulation in many cell culture studies. So to understand the mechanism and ensure the reproducibility, we try to identify the actual field at the cellular scale and the induced transmembrane potential. So the induced transmembrane potential is just the difference between the potential inside and outside of the membrane. And furthermore, we want to evaluate whether the induced transmembrane potential serves as a key indicator of the efficiency of the electrical stimulation. So towards this goal, we use the digital twin of the electrical stimulation device in vitro to inform the fine-grained numerical simulation of cell based on the 3D fluorescent image. And we coupling the macro scale with the cellular scale. And so what is the digital twin? So the digital twin consists of the model of the object, the data related to the object, and the way to dynamically adjust the model in accordance with the data. And having the reliable digital twin can make the optimal choice of the experiment in vitro, and also give us the ability to access the quantity that's difficult or impossible to measure. So recall that, like we solve the electroquasi-static equation. Oops. Yeah. And to reduce the computational effort and overcome the machine challenge in the very thin domain, we use the thin layer approximation. We have the additional term in the quick form. we D the thickness of the layer, and the square bracket describe the jump across the face. So this in particular useful in the case where, for example, we have the membrane and the nucleus envelope in the nanoscale, whereas the cell body or the nuclear plasm in the microscale. So explicitly meshing this thin layer can lead to the poor quality element, even the mesh values, and of course it's high computational time. So this is the device that we use in the cell experiment. So this is the chamber, which is called the Mobini chamber, which have 6 wells. And in each well, you have 2 L-shaped electrodes. So we culture the cell in the cell culture medium. And the stimulation approach involves the voltage driven at 20 volt peak to peak and 1 kilohertz. So how we build our digital twin? So first of all, we need to record the electrochemical impedance spectroscopy data, and then we use this data to fit to the equivalent circuits, which also consider the electrolyte interface. And then we use this impedance model to predict the voltage drop across only the medium. And then we use this as about the boundary condition to our macroscopic model. And during the electrical stimulation, we also take the image of the cell at the middle of the chamber and from the voltage drop across the whole chamber. We can determine the realistic boundary condition need to impose on the faces of the image. And then we can determine the electrical field and the induced membrane potential at the cellular scale. Yeah, so how we create a mesh. So we have the image, and from the image we do the segmentation slide by slide by combine the deep learning algorithm and also the advanced classical algorithm. And in order to mesh the bounding box, we need to do some post-processing. And so we mesh the surface using SIGA, and then we mesh the volume using NetGen. And of course, we can test different scenarios. So in this case, you have the nucleus inside the mesh, and this one without. So going for some results, so we assume that the calcium signaling will be triggered during the electrical stimulation if there is high enough the induced membrane potential. Unfortunately, with our current parameter, we don't see any change in the calcium signaling after the simulation. So more investigation have to be done. So other than that, because now with the development of the microscopy and the sensor, which enable the development of the impedance analysis and the electrical stimulation. However, there is no straightforward pipeline for developing of the realistic numerical simulation. So our work is we would like to develop a user-friendly interface to bridge this gap, and our solution based on the well-established open source software NGSolve, and people can really use using the high performance cluster. So to illustrate the software, we use the spheroid, the available data, the spheroid, and then we put it in the electrode. We put it in the micro cavity, so it has two round-shaped electrodes. Yeah, and so we are able to assign different material property to mimic the situation when you have different cell property. So, for example, here, this is 100% dead cell, and then only the outer cell is dead, and then only the inner cell is dead. And based on the numerical computed impedance, we can detect different cell state. Yeah, we can also have the electric field distribution during the cell development. And we have the problem, like for some methods, the MPI simulation, so different results based on the number of nodes used. And I'm really happy if the community have any feedback or suggestion for this. Yeah, so now I will hand over to Philip. He will continue with the different simulation.
Yeah, another application, as you see, we are a bit more from the application side. On a bit broader scale is the so-called deep brain stimulation. So we insert, as you can see on the image, an electrode into the brain and perform electrical stimulation in the brain. We do this for the treatment of different neurodegenerative disorders, including Parkinson's disease, essential tremor, dystonia, and many, many more. Also Alzheimer's, severe depression, and so on. So this has really a medical application. The issue with this is the good thing is it works quite well. We have like 250,000 patients treated globally with this stimulation devices. But the issue is that it's not understood how it actually works, at least not fully. So this is why we work on simulation for these cases, because in the patient you cannot try out everything in the simulation you can do. So this is why we built our framework for DBS simulations based on NGSolve. And therefore, I just want to show you, like, this is a different topic on different scales, right? We have the brain as a whole organ, but we also have the single neurons in the brain that has different time frames, so they happen in nanoseconds, microseconds, nanoseconds, and also on a very, very small scale. So today I will focus on the so-called volume conductor model, calculating the field distribution in the brain on a higher level. And the other stuff is mostly based on ordinary differential equation that describe the behavior of single neurons. As Vienne already pointed out, one important thing is to get a realistic model of your domain. And this is in biomedical applications most of the time based on imaging. And also from the brain, you use different images which you have available from clinical scans. So what we have usually for a patient are like MRI images. So you can see them on the left, which are segmented with different algorithms in the main tissue types, which are usually CSF, which is the fluid in the brain, and we have gray and white matter in the brain, which have different conductivities. We use CT scans where we can estimate electrode position, so we really get the target, which is essential for those applications. And also important is the DWI data, another scan performed in clinics, which give us the diffusion directions of water in the brain, from which we can reconstruct the anisotropy in the brain. So the conductivity we use in the brain is not a scalar value, it's a tensor. So we have tensor values which are important for regions where we have fiber tracts, so the electric field is not spreading uniformly, but it's spreading along those fiber tracts. Those things we take into account based on the clinical data. When we create our model, we simulate for different signals. So usually the clinical signal are rectangular signals with charge balancing, so there is no induced current to the brain, or at least it does not stay in the brain. And this we can do via our Dirichlet boundary condition in the brain. So here you see a very simple structure of a brain with the different tissue types, different colors, with an electrode inserted, and you can estimate how the potential is spreading, or the electric field is shown here actually, with different configurations of the electrode. And on the middle side you see it on the uniform distribution and the isotropic properties, and on the right side taken into account the inhomogeneous and anisotropic tissue properties. So you can see that those things really have an effect on the electric field, and therefore of course on the treatment of the patients. So it's very important to get this right here. Another issue is that those electrodes have more contacts than actually used. So you can see on the right an image of the tip of the electrode, which is inserted, and we have here most of the time 8 contacts. This is good for the clinicians because they can adjust different contacts, different settings, try out different things. But this is also a challenge for modeling because the contacts that are not used are so-called like floating potentials in the area that we model. So they are not with a fixed potential. But they are field free because they are highly conductive. Of course, there are different opportunities to model them. We could just assume a very high conductivity value, but it would lead to an ill-conditioned matrice. So what we do, we enforce zero net current via Lagrange multiplier and get this formulation over there, adding 1 degree of freedom and 1 constraint per floating conductor. So we assume that the potential at one of those floating conductors is fixed, but the actual value is determined based on the things around. This results in the following system with the saddle point problem, where C enforces the fixed potential for the floating conductors. In NGSolve, you can do this with the plateau space, so that basically uniforms all degrees of freedom within those this floating conductor to a single degree of freedom, so you can solve it with one value for the whole domain. An alternative approach, which needs data, is using the surface impedance. If this is no, we can do it via the so-called Robin boundary condition. So we have no saddle point problem and can solve it also very quickly. But therefore, we actually need the information from the clinic about the actual surface impedance of the contact, which is not always available. So if we do all this, we get some modeling outputs. Those are of course not here the focus, but I just want to quickly show you that with the electric field, we can estimate different properties that are used in clinical practice. Often the volume of tissue activated is like a spherical, or here you can see on the bottom left, this sand clock shape-like approximation of the region that is activated in clinic. But we also have like more detailed estimates seen here on the right, so-called pathway activation model, where you use these fields that we estimate, overlay them with the pathways in the brain, which we reconstruct from atlas data or from the actual imaging data, and then we can calculate which pathways in the brain are actually activated. We can trace to which region they are connected and compare this with the behavior of the patients and see, is our simulation accurate? Can we predict actual improvement? And can we help with this to predict treatment outcomes for patients? Of course, their meshing is also important because if you want to bring it to clinical practice, it needs to be quick and we need to test a lot of different things. Here, just a small overview. We use H refinement, which is of course alone not that sufficient. Also only P refinement showed some problems if we use too high refinement degrees of P refinement. But with NGSolve, there's also the HP refinement opportunity, which showed really, really good conversion for our case, especially since we know where are the tricky parts of our domain. So we know that at the electrodes, where we assume a fixed potential and then go over to the brain or to the isolating part of the electrode, we get the singularities there. And with this prior knowledge, we could implement the refinement at the edges where we need it, and get a really good conversion with a low number of degrees of freedom, which could boost our speed significantly, making it more suitable for studies with a high number of parameters and different setups and so on. So just to conclude, as I mentioned, if we want to come to clinical practice, those simulations need to be quick. We need to have efficient meshing, refinement, assigning and everything, which works really well with NGSolve. And we wrote our pipeline called OSS-DBS V2, the open source software for deep brain stimulation, which offers now this fully automated workflow. And with this graphical user interface with our colleagues using developing LeadDBS as Harvard Medical School, we were able to bring this to research practice, not to clinical practice yet. There are, of course, some other difficulties. But in research, it's already well established, even for people who has no idea about NGSolve, actually using it through this interface. That's what we wanted to present here. And if you want to see code, there was no code on the slides, feel free to check out the code or ask us directly. Thank you.
Thank you very much for this nice talk. Are there questions? Yeah.
So you, first of all, very impressive work, and I'm also very, I'm looking forward to the results of the first work because I do not have any cartilage in both of my knees anymore. But for the second part, you say you obtain like anisotropic material dependency.
Yeah.
So you basically you take MRI imaging and then you assign conductivities, like tissue-dependent conductivities?
Yes, tissue-dependent conductivities, and then we take also the DWI data, which is not that well known. It's basically the diffusivity of water in the brain, and from this you can basically derive the fractional anisotropy and get an estimate for the tensor. So you have the value, and then you multiply it by the tensor to get the actual dielectrics.
And is this continuous, or is this the data that you results and that you use is continuous, or?
So you assign it for each domain separately, so that you have those boundaries between there. Yeah.
A step from the MRI to meshing. Are you resolving the different tissues on the mesh, or are you using some kind of voxel coefficient function?
We use the voxel coefficient function for this.
Yeah.
What kind of elements do you use for the tensor part of the NGSolve? So if you do do you simulate them? So do you have to run some simulation, or do you just take the value that you have from the scan?
We just take the values from the scan. So
yeah.
yeah.
In, I don't know, an L2 or directly in a
Yeah.
Any other questions?
How did you find out about the plateau finite element space?
Yeah, that I will also.
Sorry, can you repeat the question?
How did you find out about plateau FA space?
I
think it's never not in the documentation.
I was also surprised.
Yeah.
I think they were the ones asking it. You were
Yes.
So you answered it.
Yes. Thanks to you.
Yes.
On the forum.
Yeah, in the forum, our colleague asked the question there, and we just used your recommendation. Yeah.
Now it's unmute.
Yeah.
Yesterday I have looked for it about 1 hour because I know there is the plateau FA space.
Yeah. 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 Thanks to you.
Any other questions? Otherwise, thank you again. Der Beamer, der wird mir noch so oft anstrengen. Ja. Okay. So, can you zoom? Perfect. So the next talk will be about slip boundary conditions for the Stokes problem in rotational form, and yeah.
Okay, thank you, Philip. Okay, so I will talk about some formulation of Stokes that maybe is not yet available in the Stokes repair game, but maybe it will be in the next release. So this is a joint work with Sabun from the Norwegian Research Center and with Ralf Illmeyer and Wouter Tonnen from ETH in Zurich. Okay, so let's get started. By the way, you can find the code for this work already in this shared folder that Philip provided in the email. Okay, so we will just give a bit of theory before, and then we will dive into the numerics. So this is Stokes' problem, so everyone knows it, but just to be on the same page. So the true formulation of the Stokes problem is with the symmetric gradient, and this is quite important, especially for the application I have in mind. And when the viscosity is constant, then we can write a Stokes problem in this formulation, so with this curl instead of the divergence of symmetric gradient. So this becomes a kind of Maxwell problem. And we want to discretize this formulation by taking velocity in an H-curl conforming space and pressure in H1 conforming space. We have some motivation to do that. So, for example, there is this semi-Lagrange method based on velocity in H-curl developed by Wouter and Ralph. And also we are extending this method to MHD. And this requires the velocity in H-curl. But maybe even more importantly, if you want to preserve the so-called cross-helicity in magnetohydrodynamics, which is a very important invariant of the system, it seems that it is really mandatory to have the velocity or some projection of the velocity in an H-curl conforming space. Okay, so sleep boundary condition means that we want to impose this tangential normal component of the symmetric gradient on the boundary together with the U dot n condition, the classical non-penetrability condition. And so, of course, you can already imagine that this condition is not immediate with our rotational formulation. And another important thing to keep in mind is that when we have this boundary condition, we have possibly we have a non-trivial kernel when the domain is generated along revolution along an axis. And so, if we change formulation, we want to make sure that this is maintained by our formulation. So how to write this sleep boundary condition in the rotational formulation? So firstly, we have this identity, so we can show that this sleep boundary condition are actually equivalent to this new set of boundary condition, which are kind of Robin boundary condition for the velocity. And the interesting thing is that we see the appearance of the Weingarten tensor, which encodes the curvature information on the boundary as the Robin parameter of the boundary condition. And also bear in mind that since the curvature can be positive or negative, this term doesn't have a sign. Okay, so now I will directly jump into the discrete formulation. So as I said before, I want to have Nedelec. Let's take first kind, but I can also do second kind, but just to fix ideas, let's take first kind for the velocity. And standard Lagrange elements for the pressure. These are my bilinear forms. So we have this A is this curl bilinear form plus this term on the boundary. And as I said before, this term doesn't have a sign, so we cannot just say, okay, this helps with the coercivity, but we don't know what it does. And then we have the bilinear form B, which is simply the bilinear form related to the weakly divergence-free constraint. And then we just have this additional norm that is helpful for the analysis of the discrete problem. So our final discrete variational formulation is the following. So it's a standard, more or less, saddle point problem. Okay. What we can say about well-posedness and our estimates, so we can say that under reasonable hypothesis, we have an H-independent in-sup condition for the bilinear form A. So this part is fine, but then we have an H-dependent in-sup condition for the bilinear form B, which H that goes like H1 half. And this causes that then when we go to error estimates, we have optimal error estimates for the velocity, so this h to the power of r. Remember that we have chosen Nedelec of first kind, so this is the best that we can hope for. And then we have, we lose half an order of accuracy for the pressure because of this h-dependent in-sup condition. Okay, now let's go into the numerics and implementation in NGSolve. So what we have, if we write our system of equation, is what is called a nested saddle point problem, because we have these bilinear forms A and B, as I described before. But then also we have to impose the pressure as average 0. So we need an additional matrix, which is in practice a vector, to impose this condition. So this is the resulting system of equation that we want to solve algebraically. And so what I'm doing here, maybe it's probably not the best idea, but I decided to compute the Schur complement S with respect to the first saddle point problem, and then so that I reduce the system only considering the pressure and the associated Lagrange multiplier. And then we solve the resulting system with GMRS, and then we use a preconditioner that project onto the kernel of this C-matrix. So in this way we avoid solving the standard point problem. We can directly solve this SP equal G linear system using this preconditioner here. And then to do this we need also a preconditioner for the Schur complement, and for that I'm taking the stiffness matrix of the Lagrange finite element. Don't ask me why, it works quite well. Okay, so this is the linear algebra behind it. Okay, so this is how I compute the Weingarten map. Remember that I need it, and actually I'm computing using this this code that was done by Mikkel and Teufel on how computing the distributional Weingarten map. And this is, I mean, I will not go into the details. Maybe, I don't know if maybe tomorrow you will hear a bit about this. But so, I mean, the idea is to compute it using this jump in the angles that we have at edges. And then we have to, since what we get is a distribution, then we have to compute like a lifting using an inner product. And in the end, we get a coefficient function that approximates well the Weingarten map. Okay. Okay, then I will go fast on this part is quite standard, so finite element spaces, right hand side, nothing particularly fancy here. Okay, but by linear forms. In this here we add the term, the boundary term with the Weingarten map that we can compute with that function. Everything else is quite standard for this stiffness matrix as a preconditioner that I'm using here. I have to regularize it a little bit because remember that otherwise is singular. Okay, and then as I told you, this is how you solve this linear system with GMRS with the preconditioner I have explained before. So this is just more or less everything that I've already explained previously. And okay, so let's look at some results. Here I am considering a three-dimensional standard convergence test with manufactured solution, so order 1 and order 2. As you can see, the GMRS behaves quite well in the sense that you can see that the number of iterations, of course, increases with when the match gets finer, but not that much. The time is at some point for order 2 we reach a threshold in which probably the factorization, because to compute the Schur complement, of course I need to factorize the matrix A, and this is probably the most expensive part of the algorithm, and at some point we reach a threshold in which this becomes quite expensive. And then we have the convergence order that as predicted. So here we have a little bit even more than what was predicted, but it's probably because some pre-asymptotic stuff. But then for the pressure you can really see this 1.5 convergence rate that reflects this H-dependent IMSUB condition. Some maybe more interesting tests to have some nice plots. So this is a flow around a slippery sphere. So we have this sphere on which we impose this slip boundary condition, and then the domain is a cube around the sphere, and on the rest of the cube we impose the Clay boundary condition. To see how to impose the Clay boundary condition in this formulation, you will hear next talk by Camilo. And okay, so to conclude, I'm not really 100% satisfied with the implementation here because the matrix A is invertible only on the kernel of B in principle, and now I'm adding a regularization, and then I'm factorizing it with a direct factorization, and this is quite expensive. And moreover, I am using GMRS, and GMRS, we know that it stores all the iterates, and therefore it, from the memory point of view, is quite expensive. So I would like to improve this method by doing the following changes. So I would like to solve the entire system instead of using the sure complement, and to use minres instead of GMRS. And also I need to find a good preconditioners for the entire system. And with that, I've concluded. Thank you.
Thank you very much for the nice talk. Yeah, please.
Did I miss something? Why are you not symmetric?
The matrix is symmetric, yes, but I'm not sure. I mean,
I thought about the positive definite.
yes, this is. I'm not 100% sure it is, and also the problem is that again, if it is only on the kernel of B, so not on the whole space.
But you regularize, so.
Yeah. But if I mean, I try to compute eigenvalues with NGSolve. I get everything positive, maybe very small or very large, but everything positive. As Cholesky factorization works, the conjugate gradient, I think it doesn't converge. So probably it's very conditioned.
Okay.
You plan to solve the entire system without forming true complements.
Yeah.
Do you know the mapping properties of the individual subspaces? Do you have a big in subconditional?
I mean, I don't have it explicitly, but I can.
Then it's clear how to do it.
Okay.
Yeah. More questions? Okay, then thank you very much. Then we will now see more on boundary conditions. Thank you. Ui, Maus. Ich hoffe, es geht. Ja. Auf der Seite wahrscheinlich. Das kann interesting. Achso, du ist da besser. Da hast du die Maus hast, dann ist vielleicht schon das Stift, oder? True. So the next talk will be on Nietzsche-based enforcement of Dirichlet boundary conditions for the Hodge-Laplacian using NGSolve.
Yes. Hello together. As I said before, I'm Camilo, and I did the master thesis formerly with Joachim, but I was mostly supervised by Enrico, who presented earlier, and Wouter under Professor Hippmeier, also more formally. And I'll talk about the Hodge-Laplacian. Short outline, I skipped this. The scope of my thesis was, I started with the implementation in NGSolve for the Hodge-Laplacian. So 1 forms, 2 forms, 2D and 3D. And I'll try to explain to you in a bit what this is about. Then I tested for convergence rates to see if it would actually make sense to prove something. And as it turns out, it makes sense to prove something. We continued with the mathematical analysis, proven well-posedness, consistency, and generalized theorems for differential forms. And then also derive a priori error estimates to compare with the convergence results. And I'll try to show what we've done. So most of you probably know the RAM complex, the classical one here in the middle, but maybe people that are not introduced to finite element exterior calculus is that there exists also the same for a so-called the RAM complex of differential forms, and we have isomorphisms that help us simulate those in NGSolve. So if we want to simulate 0 forms in NGSolve, we can take the H1 space for 1 forms H curl space. I encourage you to accept these finite element exterior calculus objects as just abstract objects now, because you will see that it's not really necessary right now to dive into the specifics of it. So the exterior derivative, which basically makes this complex, is exact and commutes as well with the projector. And then also we have the formal adjoint of it, which is called the exterior co-derivative, which commutes as well. And yeah, we have the projectors available as well. We have the their adjoints. So if we want to have the exterior derivative from h curl to h minus 1 to h1, we take the negative divergence, for example. So this is the abstract Hodge Laplacian with the Dirichlet boundary conditions. So these are not the standard boundary conditions. So for example, now if you go back to the round complex, so say you have one forms, you would model it with h curl. And this trace omega you can simply imagine as the trace. And what is the trace of an h curl function? Take the Nedelec elements, that would be the tangential trace. And Hodge star, encourage you again to accept it as an abstract object. It basically the 90 degrees rotation of it, then you would have the normal component. And how to enforce the normal component of a Nedelec element, I will try and show you. So the motivation why to study is mainly to contribute to academic literature. There are some applications, but it is difficult to motivate them if you consider classical applications. For example, compressible flow or elasticity, they are already well studied, but you could potentially solve it with them. So I would say mainly to contribute to academic literature. And so these are the Dirichlet boundary conditions, as I said. So because for one form this would be tangential, and then here the Hodge star of omega would be the normal trace. So together that would be full Dirichlet vectorial. And Arnold and Jay as well have already contributed to this. The problem with Jay's and this paper was mainly that they do not satisfy the round complex, and they have only results in 2D, and they would potentially, so Wang et al. With a quite recent paper, they have another approach. They just introduce an additional variable, and they have now 3 fields. I only have 2 as a mixed method. And yeah, like I said, linear elasticity and compressible Stokes would be potential application, but yeah. And why do we treat it in the exterior calculus framework? Because, as I will try to showcase you, this provides a generalized analysis framework that gives you nice results for a family of methods, not only for, as if you would prove it, for example, say a mixed method in H1 H curl. But we also have then the same result for H curl H diff mixed method that yields the same results from the same proof. And to introduce the mixed method, we introduced the auxiliary variable exterior derivative of omega. If you consider back the round complex back here, so if you take one forms, that would be minus the divergence. All right, so Arnold in his manuscript Finite Element Exterior Calculus, the big book, they introduced this mixed method, like I already said, and you would get this. And with my boundary conditions, also considering non-zero Dirichlet boundary conditions, you would get this. And now I'll try to bring closer to you why I told you to not be confused by exterior calculus. If you would set k equal to 1, and by the isomorphisms, it is simply just a vector Laplacian. And maybe you also recognize it from the talk before. It is essentially the same, just not divergence of u equals 0, but divergence of u plus p, because we introduced this via the auxiliary variable. And now what would we do in finite element classically? Multiply by test functions, you get this, and then introduce these 2 trace operators to integrate by parts this first term to get this, and integrate by parts this second term to get this. Now normally if we would incorporate the naturally occurring boundary conditions, and we would take this term to the right hand side to set it 0 for Dirichlet or non-zero for non-zero Dirichlet. But here we keep it on this side because this is the boundary condition that Arnold treats in his book and is relevant for electromagnetics, but we do not want to. So we keep it here for now, and you'll see why in a bit. We introduce now the Nietzsche method. So we have this term that arises by integration by parts earlier, and just classically according to this chapter in Ernst's book, the second one I believe, chapter 37, you introduce first the symmetrization term to have a symmetric bilinear form, and then you introduce so this one, and then you also have obviously on the right hand side a term that you need to add for non-zero Dirichlet, and then you introduce this Nietzsche term, which is just a penalty term that you need to you pick a sufficiently high parameter, and then again as well on the right hand side for non-zero Dirichlet. Then we define the bilinear forms. As you can see, this is quite a similar bilinear form as Enrico has showed earlier, and then you get this big bilinear form B, where you sum up all the these bilinear forms, and you get the right hand side F for these would then obviously vanish if you have 0 Dirichlet boundary conditions. But this is now quite interesting because now we have basically Dirichlet data incorporated into the system only via integrals, not via equipping the spaces. So these are the problem statements now. So we have a mixed method H curl and H1, big B equals F, and we also have the same for finite element exterior calculus like this, and we also have derived the proofs in this abstract framework, which gives us the results for the family of methods. How would we prove well-posedness? Well, we take the big inf sub and you choose a suitable norm, which we have done. If you want, I can show to you later what that norm looks like. And we were actually able to prove continuity. Unfortunately, proportional to 1 over h, but still continuity. And we have the same result also for general differential forms, again proportional to 1 over h. And we have a stability result independent of h for the one forms case. The one forms vector proxy case would be H curl H1 mixed method, which is still essentially a vector Laplacian with Dirichlet boundary conditions. And we also have the same stability result independent of h for the general differential forms. We also have a priori error estimates. So now bear in mind the one that, so this is already a convergence results for several methods. That is like highly suboptimal, right? This is R times minus 1.5, it's not so good. But for 2D1 forms, we came to the same convergence result as Jay and Arnold did back then. Also with one of their function analysis results they used with the projector. So now to the numerical results. Classical standard way of showing conversions with like plugging in smooth test function, a smooth manufactured solution, assigning the values. I visualize now order 1 and pick the penalty parameter equal to 12. And here on the top you see the analytical solution, and down here you see the discretized solution. As you see already with quite coarse mesh and low order we really have, and you also see the non-zero Dirichlet boundary data. And now, so you see we are an entire order better than the a priori error result. Oh no, I'm sorry. This is actually the coinciding error result. So as I said before, for 2D1 forms we have R time R minus 0.5 in this X norm, which is a norm on the product space. And this is actually optimal a priori error result. In R3 we do the same, just a bit more involved manufactured solution. Assign Dirichlet data, again 12. And then you see here on top, you see the analytical solution. And here on the bottom, you see the discretized solution. And again, here already for quite a coarse mesh, you see that we resemble the analytical solution already quite well. Here I cut the unit brick in this way, and here in the middle you see the cut sections of the cubes for the according discretizations. And here again we have the X norm, which is the product norm. So here on top is the actual X norm, and the other three plots are the components of the X norm. So maybe just have a look at this one. So, and as you see, we are an entire order better than the a priori error result, which is bad because our result is suboptimal, but it's also good. That means we still are able to close, we're potentially still able to close this gap. And now, as I said before, since we have the results in finite element exterior calculus, generalized differential forms, we can just go ahead and employ this mixed method HDiff and HCurl. So that would be for 1 forms and 2 forms. For 2 forms and 1 forms. And we can just employ this method, and we know that it's stable. We know that it converges at least with r to the 1 minus 1.5, but as we'll see, it converges better. We test the same manufactured solution as for the other case, but with now a different mixed method. And we see here it is the exact same solution of the vector Laplacian, a different auxiliary variable. Now, obviously, because our auxiliary variable is now vectorial and discretizing, like it's a different p, of course. And yeah, for quite a coarse grid already, you see resemblance of the numerical solution, of the analytical solution. And again, we have the same convergence rate, so r minus 0, r to the 1 minus 0.5. And it's again suboptimal, but yeah, we can potentially still close this gap. Now I'll show you some NGSolve code. You see it is not very crazy. And on the...
Yeah, can you zoom in a little bit?
Yes, that's too smaller. Fortunately, I supplied the NGSolve code in the... Wait a second.
No, in the VS Code, just show VS Code and do Control plus, then that should be bigger. No, another within the genau.
Yeah. Nope. View.
Zoom in.
Zoom
Control.
in.
Numpad plus. Numpad plus.
Is it better?
One more, I think.
One more. Appearance. Zoom in. All right. So we have this. So here you can actually download this and play around with it. So re-entrant corner geometry in 2D. And if you run it, so this is now without manufactured solution. This is now just the Dirichlet boundary conditions with, let's go to the code first. So geometry, generation, I assume is okay. 1 forms 2D function. So this is, so it's important to note that actually this method only works with Nedelec of first kind. And yeah, in 2D, obviously, you have to take into account that you have to treat the, so the curl will yield a scalar. And yeah, this is essentially just a copy-paste from the methods that I showed you. And then you just iterate over the boundary names and add the boundary integrals that I showed earlier. So here, maybe this one is interesting. H is the the local mesh size, but we assume uniformity in the proofs. And what is also interesting is how I enforce the tangential trace in the Ravi-Thomas elements or the normal trace in the Nedelec elements. So we use the skeleton. So basically we abuse DG methods to apply the Nietzsche term. So here, so this would be, so gamma parallel, that is the tangential one, and gamma parallel is also the tangential one. So that is fine. But for example, if you look here, we have G times the normal one. That is fine. That is the data. And in the same way, we do it for the two forms. Yeah. And please feel free to download it. Feel free to ask questions. And yeah, that's been it. Thank you.
Thank you very much. Questions? Yes.
The continuity gap of h to the power minus 1 is it clear?
I'm sorry, there's no. You mean?
In this,
You mean in the error rates or?
no, well, in the analysis, before the error rates, you had a continuity result and it had
Yeah.
power h to the
Yeah.
minus 1. Is it clear from which space this stems or from which subspace?
Yeah, basically we use a bunch of inverse inequalities to prove the things, and it stems from the inverse inequalities on the from the H1, but we also use inverse inequalities in the H curl space as well. It is if you want.
For both.
Sorry.
So it's there due to both inverse inequalities of the one and the other, and it's unclear which subspace has eigenvalues, singular values of the order 1, and which has.
That's a good question, but essentially we designed the this hashtag norm is the same norm that Enrico and Wouter used in an earlier work, which is not the one that he presented today. But this X norm, which is the space, which is the norm on the product space, has this h squared here, and in order to get to this h squared, here is the gradient of Q. You need to apply the inverse inequality, and this inverse inequality yields the 1 over h.
Okay. Other questions? No, then thank you again. Dein Adapter. Darf ich den ein bisschen drüber schieben, dass das dann nicht so runterhängt. Da müssen wir noch irgendwas. Ich glaube, wir müssen noch irgendwie verbinden. Keine Ahnung, wie das da geht. Windows. Who knows? There is a... No. Who knows how to use a Windows laptop? Or, no, it was... No, it was just not plugged in. Okay. My bad. Great. My bad. Okay, now Control L. No.
Bildschirmpräsentation, will ich hier?
An sich das dritte verwendet vielleicht.
No, no,
Awesome.
it works.
Okay, yeah, so our last presentation on fluid gel interaction. Thank you very much.
Yes, so it's my pleasure to welcome you to my presentation about fluid gel interaction. The project was developed as part of my bachelor thesis. I'm currently studying robotics in the University of Applied Science in Zurich. The idea for this project originated from a capacitive measuring cell used by a company based in Winterthur in their precision inclination measurement device, which has a resolution of 1 millimeter per kilometer, so it's really precise. The cylindrical sensor cell consists of a gas-filled cylinder with a membrane spring suspended in its center. This membrane spring is free to move within the gas cylinder. When the device is tilted, the membrane spring shifts to a new position, behaving like a pendulum. Its motion is dampened by the displacement of the surrounding fluid. Here you can see the membrane spring with its spiral slits, and it's mounted between these two electrodes. The position of the membrane spring is determined by measuring the capacities between the outer electrodes and the membrane spring itself. The difference between the capacities is converted into the position of the spring and the inclination of the sensor. However, it takes approximately 5 seconds for the spring to settle into a stable position before a reliable measurement can be taken. To optimize the response time, the idea was to model the entire system. The entire 3D model I used to analyze the system consists of the spring domain, denoted as gamma S, as well as the overall omega domain where the fluid is defined on. The boundaries gamma outer with Dirichlet boundary condition 0 for the fluid means that the fluid behaves like a closed system. Gamma fortification is the Dirichlet boundary condition for the membrane spring. The two-dimensional model was created by me to test certain aspects of the fluid coupling with thin structures. In the 2D model, the spring represents the red marked beam in the center of the model. At the top end of the spring, there is a region where fluid exchange can take place. The spring is fixed at the bottom end with Dirichlet boundary conditions. The fluid is defined through the entire rectangular domain omega. It's difficult to analyze thin structures using classical elasticity models. The spatial discretization composed by triangles and polygons must avoid overly small angles. When the angles become too small, the problem becomes poorly conditioned and the error increases significantly. Thin structures therefore require very fine discretization, which leads to a very high computational effort and time. To circumvent this problem, so-called shell models are used. In these models, the structure is reduced by its thin dimension. This solves the discretization issue. In return, the shell formulation is more complex than the conventional elasticity models. Here you see a 3D model of the membrane spring and how fine this discretion gets if I just divide the thickness by 4. And this is a 2-dimensional model with a discretization, which is much coarser. In shell models, stationary points of the internal energy functional are sought. The internal energy consists of three components: the bending energy, the membrane energy, and the shear energy. These energy terms can be solved as a nonlinear problem, but also can be linearized. Additionally, the shear energy is sometimes neglected. In my project, I used the Reisner-Mindlin shell model. This is a linearized shell model that takes shear energy into account. The same dimension reduction can be done in a 2D model. The two-dimensional beam is reduced to a one-dimensional domain, and the Euler-Bernoulli beam equation is applied to it. As you can see here, the beam is the domain in the middle, and now it's reduced to a one-dimensional domain. The beam equation is a linear differential equation that seeks a one-dimensional representation of the deformation. Since the problem is of fourth order, as it's handled with the substitution. The second partial derivative of the deformation is substituted by the curvature and solved as a system. The point for fortifications, this is the lower red dot, serves as Dirichlet boundary condition for the deformation, and the upper red dot, the free boundary, serves as Dirichlet boundary condition for the curvature. To account for the deformation of the fluid domain in the Navier-Stokes equation, the deformation of the spring must be transferred to the fluid domain. For this purpose, a modified Laplace equation, which includes a stiffness weighting term, is solved on the fluid domain. On the spring boundary, I use Robin boundary conditions in form of a penalty term. With a high weight on this penalty term, it converges to a Dirichlet boundary condition. The Navier-Stokes equation used for the fluid contains some special features. The spring represents a flat structure with no thickness. Therefore, the two chambers of the fluid do not have any spatial separation. However, they exhibit different pressures. As a result, the pressure trial function must be capable of discontinuities. For this reason, discontinuous L2 functions are used for the pressure. The Navier-Stokes equations are solved using modified Taylor-Hood elements. The additional degree of freedom included by the discontinuous pressure are controlled by increasing the inner order of the fluid velocity H1 trial functions by 1. The time-dependent deformation of the fluid domain in the Navier-Stokes equation is accounted using the arbitrary Lagrange-Eulerian formulation as already implemented in the fluid structure interaction on the NGSolve 24 website. The velocity of the fluid and the spring at the boundary of the spring is coupled using an additional Lagrange multiplicator. The entire model is formulated in one bilinear form using the trapezoid method. To relate the model back to the concept of the project, the capacity difference between both sides is computed at each time step. For this purpose, the potential between the left electrode and the membrane spring and the right electrode and the membrane spring is calculated, and the capacity difference is derived of it. but enough theory for now. Let's take a look at some results. First, we examine the results of a simplified 3D model. In my project, I use a direct Newton solver for the entire system. However, it would be interesting to find the iterative solver for the problem. Maybe something interesting for you. Instead of cutting spiral slits into the model spring, into the membrane spring, only a central hole is introduced to allow fluid exchange. This allows a much coarser discretization of the model. Instead of tilting the model, the force vector is rotated. It is applied to the model at an angle of 45 degrees. Here you see a visualization of the flow and the deformation of the spring. In addition, the position of a point on the edge of the inner circle is recorded in the X, Y, and Z direction, as well as the capacity difference. In the upper left, you can see the deformation in the main deformation direction. It is clearly visible that an oscillating behavior occurs, which is dampened, and the spring settles at a specific position. Below that, the capacity difference is recorded. It closely follows the deformation in the main deflection direction. On the right side, the displacement in the X and Y direction are plotted. Now we have the same model, but with an increased viscosity, which should lead to a higher damping. The deformation recordings of the point clearly shows that there is no longer any oscillating behavior in the main direction, and you have a higher damping in the Y and the X directions. Now the same thing with the 2D model, with the Euler-Bernoulli beam. Here you have the pressure on the right side, and you can clearly see in the pressure that discontinuous elements are used in the area of the spring. This is with a lower viscosity, so we have much turbulences in the flow. And after that we will do the same experiment with a higher viscosity. On the left side is the deformation in the X directions. It is the deformation is a one-dimensional representation, so we have just one plot for the deformation. But also here you can clearly see that this is a oscillating behavior with the damping, and the capacity difference follows the deformation. Now with the higher viscosity, the oscillating behavior nearly disappears. The recordings also clearly show increased damping. And what also clearly is shown is that the capacity difference cleans the higher order oscillations of the deformation. Finally, I would like to thank you for your attention. I hope the presentation was interesting. And especially I would thank Dr. Simon Stingelin for his outstanding support in the development of the project.
Thank you very much. Very impressive for a bachelor thesis. Are there any questions? Yeah?
Can you again explain the application?
Yes, this is an inclination measuring tool. Maybe you see it better on the first side. These are measuring devices which are used special for dams, which has to be really precise. And yes, you have these problems that the measurement needs a time of 5 seconds to get a reliable result. But the whole system could be applied to many other systems, like a fluid cell, or wings of an airplane, or a delta glider or something. Yes.
Really impressive results. It looks really nice, and I think it's the first application in NGSolve that couples shells with the fluids, right? No?
For the shell, you use Helen Hammer Johnson type method, which is edge-diffy on the surface, I think. The one you cited with Michael Neuteufel. You're discretizing the membrane spaces.
With the Reisenwindling shell, like you did it on.
I think it's a very intuitive shell element. So shell elements are often quite complicated, but with this mixed formulation, you have a good understanding of the bending stresses, or with the edge-diffy variable. Yeah.
Okay.
Other questions? I have maybe a short question. So you say here thin spiral spring in a gas cylinder. So the real life device, is there a gas or is there a liquid?
Yes, no, it's a gas in the real life device. And a really special material for the spring, which is which has a really low A module.
Mm-hmm.
But I don't know exactly what it is.
Okay,
so
but the viscosity is probably very low.
Of course.
You still model it like a fluid. Okay.
Yeah.
All right.
And what's the size of this device?
Like this, like 5 centimeters.
Okay, sorry.
I think I've never seen it in real life. We haven't any cooperation with the company. We've just done this for interest.
The diameter is about 2 centimeters.
Okay.
Because you have like real measurement data to compare to?
No. It's.
It would be interesting how close you can get.
No, we've just.
had some measurements, but it's a long time ago, and I have no doubt actually. But that would be very interesting, because the point is they were very interested in speed up the measurement, because they use this sensor for production of these marmor plates during the graining process. And if you take several hundreds of measurement points with 5 seconds, if you can speed up it to let's say 1 second, that would be an increasement in production speed, which would be very interesting. But we can see from the simulation that wouldn't be very easily. So our first answer, so many years ago, was to use a simple spring damping network, but this is not enough to model it exactly enough. But maybe quite interesting application. I think it's a nice application for multi-field simulations.
Definitely, yes. It's very nice. Okay, then
Thank
you
you.
again. Could have used 10 more minutes for the coffee break, but
Thank you.
very nice work. Okay, so, wo ist das jetzt? Bevor ich da einen Blödsinn herzeigen.
So, good. Is it just me, or do you also see some shadows of the presentation sometimes? Okay. Yeah. That one as well. Yes. Okay, so we have now our lunch break. We thought about having a longer lunch break so people can talk to each other and discuss code or other things. Feel free to go out, and you can leave your stuff here. I will be back at 1 o'clock, so if you want to come in back, I will close the doors. There is on the program, there is a Google Maps list. You can click here and it should show you some locations. So we are at the moment here, and a very short walk just over here there is this blood Mensa. So we have been there yesterday. It's a very nice Mensa with quite good food, just vegetarian food. But there are also some other places that I have marked. So here is a very long street where there are different options to have lunch for. And there is also the standard Mensa of the university here in this tower. Just a short walk over there. So as said, I will be back at 1, and see you at 2 again, latest. Edmond.
Now at the next session, Philip and his team, Jan and Edmond are presenting the dream work, the dream complexity solver.
Dream
So
team.
they explain what they're doing, they present some theory behind, and have also your computer up, you have examples where you can try it.
Exactly, exactly. Yes, so thank you very much. I hope you all had a good break. Yeah, so this is the dream team that comes from Jan. What is this all about? So why is this called a dream solver? The idea of originally, or still is, that we wanted to do some direct area acoustic simulations. Yeah. Are you going to talk about how to install and this stuff, right? Okay, so by the way, you should be able to find here in the material session, you have here this, where Joachim is exactly right now. You should have the link to this documentation. So what is this all about? This was, or this is the original, somehow the goal of what we were interested in. We wanted to do this aeroacoustic simulation. So you have here a flow around this very small cylinder that you can barely see because of the resolution of the beamer. And on the right side, so there is a flow from the left to the right, and you have this vortex street here, yeah, and then we know that there's, one knows now that there are some acoustic waves produced. So these are given on the right hand side, and what I really liked here is that one can even see a little bit this Doppler effect. And so what is this package all about? This is a viscous phenomenon. So what was our goal? Our goal was to somehow derive a compressible solver by means of a hybridized discontinuous Galerkin method. Now it already developed a little bit to somehow a bigger project where we also wanted to have a nice to use interface, particularly to get into compressible flows. And because, at least from my perspective, it was a little bit tough at the beginning to get into this topic, and this should somehow help a little bit. So there are some key features on the bottom here, what is nicely, or what you can nicely do. Particularly there's also work in progress, so yeah, I academically grew up with in the incompressible world. So this is something that we are also working on to use this solver also for the incompressible flows. And there will be a session on Friday also where we will show you how to do this actually in this dream package. Besides that, I will now mainly let Jan, so the PhD student who is working on this project, and Edmond, the postdoc student, who are working with me on this solver. I will mainly give them the audience, and
Thank you, Philip. So, welcome everybody to this after lunch session. It's gonna be interactive, so we will give you 3 tutorials afterwards, so pretty chilled. Feel free also to interrupt, such that it's more interactive. We will mainly go to the documentation, since we were in the last 2 months actually trying to update as much as possible. So there is an installation. Sorry. What is this? Yeah, sorry, Max. Thanks.
That's why I'm here.
Thank you. Thank you. More support. I don't have a Mac. I mainly develop on Ubuntu, so also the installation, we only tried it on Ubuntu, on Linux, and on Mac. I just realized now there are some people with the Windows, so sorry about that. I hope during the first tutorial, I will give you 10 minutes for the tutorial, so we can maybe try to get it running there. Yeah, it's just should. I will call you. So So you should, by now you should have gone through the installation. I personally love to have a virtual environment. I know just to have a separate development environment. You can download it, our Git repo. For the moment, we don't have a pip package. Maybe in the future we will. And yeah, follow the steps. Again, if there are problems, I hope we can fix them during the first tutorial. So, before we dive into the solvers we have already implemented, so Philippe already said we have a compressible solver, but in the last 2 months we also developed a scalar transport solver, which Edmund will talk about, mainly for testing reasons. I want to talk a little about the structure of the Dream solver. And again, is this?
Just press on.
Yeah, what the hell? So, like Philippe said, so we are mainly working 2.5 years now, I think. The project started for, like, we wanted to have a direct numerical acoustic simulations, so which means that we have the compressible flow equations, which I will show later, which are highly nonlinear equations, transient, because we are interested in the acoustic effects. So we definitely have some time stepping in it. And these are, like, let's say, very long-lasting simulations. So Philip showed you the picture of the cylinder around the flow. It's relatively a large domain for such a small, actually, body in the air. So it takes a lot of time. And while we started going through literature, there are like a million ways how to working variables you can choose, a lot of configurations, especially because in the first year, our goal of the project was to develop non-reflecting boundary conditions. And yeah, once we went into that rabbit hole, we saw that there are like a lot of boundary conditions one can implement, especially with a lot of parameters that fall from heaven. And it's kind of hard to keep track. If you do a simulation, which parameter did I use? Which time step did I use? Which Riemann solver? And you see, there are a lot of configurations.
And unfortunately, very badly documented in the papers.
Exactly. So for us, so that's when we started realizing, okay, if we start doing these simulations, we want to have at least a package where we can, for us, see which configuration did we set, which parameters did we set, and so that's how slowly this Python package, it's a purely Python package, so it's you don't need any, I think, NGSolve add-ons for it, developed. I tried to synthesize now in the structure. Again, it's a work in progress, the documentation, so there is no, but I tried to synthesize now in this 50 lines of code, more or less the essence of the Dream package. I'm gonna just, can you see it in the back? Wait, let's do it so. The essence is that we provide you some interfaces. If you would like to forget about it. So you have your CFD solver, right? You have your equations. You have your favorite CFD solver, and what you eventually would want to provide to your CFD solver are some configurations. You have if you think about the incompressible Navier-Stokes, you have your finite element method to solve this, the incompressible Navier-Stokes, and you provide the finite element. It could be a Taylor-Hood, it could be a P2, P0, but that's up to you. It's a configuration for the moment. We have also different routines, time routines that you eventually can set. Maybe you want to have the Navier-Stokes in a stationary mode. You want to use a transient routine. I will go through this later. But if, for example, there is one configuration that if you want to set the Reynolds number. We see a lot of Python features here. So we have this ETA dream configuration. I don't know if you're familiar with it. These are these properties in Python. So you have a getter and a setter usually, how you set values, how you get them. And we decided to go for this interface mainly for two reasons. The first one is that, like Philip said, we can doc with this Python, with these properties, we can document what we intend to do. So we can automatically add this doc string here. I will show you later how it looks like, such that it's clear for everybody what is our intention. And usually, if you use an IDE, you can see it while programming. It should be, for me, for Visual Studio, it automatically gets formatted. And the other reason is because of the setters. We can obviously check, hey, did I provide the correct value? Because if a user eventually would want to provide a Reynolds number that's smaller than 0, smaller equals 0, it doesn't make sense. So these are the main reasons why we decided to go for this style. Yes. Why dream configuration? This is, again, it's just a property. You have a getter and a setter, but it's for us that we can decide what is a user configuration that somebody can set to run a simulation and what is not. If we now go down to the finite element method and transient routine, I gave you here again, it's a pseudocode, but I think it's kind of intuitive because it follows more or less the guidelines that Joachim showed now this morning, or like how I used NGSolve for the past 4 years when I wanted to do a simulation. So yeah, my finite element should so when you start a simulation, the first thing you're going to do, you're going to initialize the finite element space. You're going to initialize the try and test function, the grid functions. Eventually, if you have a time scheme, you have a transient simulation, you're going to initialize those vectors. You're going to set the boundary condition, set initial conditions, and assemble all the symbolic forms. These are the usual steps that I followed. I hope you too. I mean, to set up the system. So that's an interface from our so that we provide this from Dream. So I mean, I heard yesterday that we're gonna present on Friday something. So on Friday, we're gonna follow these. So we're gonna overload these functions in order to implement eventually a Taylor-Hood element. But again, this is an interface. If you adhere to this interface, the other features of Dream should also work, hopefully. And remember, we had a member here. Transient routine. This is then also, I think, a very nice feature of Dream, which is the solution routine, because again it follows the example that Joachim showed today of the Navier-Stokes equation. This is so we start our solution routine. We get our scheme that we want to. We assemble all the matrices. So at this point, we start assembling, allocating memory. We initialize all the input-output operations. This is something that we automatically can like export to VTK, export grid functions, thanks I think to Christoph's VTK writer. And then we start the time routine. We solve the current time level. And that's it. So in theory, and we save all the outputs or redraw. This is, I think, one of the nicest features of Dream. So this routine is already implemented. If you have your finite element, you adhere to our interface, this routine automatically runs in the background. There are more features, but I think for now this gives a little bit an insight of how we structured more or less. I'm gonna show you the how eventually these doc strings look like then when you do it with Sphinx. So we go. Oh, Jesus, man! What the hell? So this is, for example, the compressible flow solver we were talking about. We have the finite element. We have the Mach number. We have the Reynolds number, Prandtl number. So all kind of configurations you can set where we have a getter and a setter, and we tell you, you did this wrong, this is not available, such that you have a nice interface. Yeah, that's it for the moment from my side, from the structure. I think now I'll hand over to Edmund, who will talk about the scalar transport, the module he implemented for now.
Thank you, Jan. So I'm Edmund, and what I'll be doing, if I remember correctly, is Jan basically gave you an overview about a dream, like essentially the core of why we do things the way that we do it. And obviously Philip told you what is the ultimate purpose and what we're also working on. What I will do is try to fill the gap between this and hands-on examples. So I will walk you through a simple scalar transport equation. It's a linear convection diffusion. So we will go first with like a pure convection equation in 1D, and then we're going to do a 2D convection diffusion one. We'll not actually do it, I'll just show you how to actually interact with Dream on such simple examples, because everyone is pretty much familiar with this. And then I'll basically introduce the Riemann problem very quickly, and then I'll give it back to Jan, because he's going to be doing the heavy lifting in terms of the actual hands-on tutorials, right?
Yes.
All right. So, cool. So, just to be on the same page, all right. By the way, this documentation is online, so you can all literally see it.
Can you
zoom in? Okay, so this is just nothing special. It's a linear convection diffusion, temporal term, convective term, and elliptic term, diffusive term. Okay? So the idea is we're interested in high order methods also. So that is something I want to point out, but it's not exclusive to that. So let's start, for instance, with a simple scalar wave equation in 1D. So this is our fancy equation.
Can you zoom?
Can I? Oh, it already resets. Interesting. So this is a simple scalar wave equation. There's nothing special going on, no diffusion. This is the domain. It's a 1D mesh, of course. And the wind velocity is 1. Nothing special. We have our initial Gaussian profile, and the idea is the actual solution should be just we're shifting the wave towards the right in this case by speed p, which is 1. So in order to start interacting with Dream, we do the usual stuff first and foremost, like NGSolve, the usual suspects, we import them from NetGen, whatever we need to. But for Dream, in this particular case, for instance, what we need is, so we need to import initial for the setting of the initial conditions. We need transport fields because, well, this is a transport solver. We're not doing something compressible yet. And this is basically the actual solver. And the usual stuff, which pretty much if you've worked with the NGSolve, I guess you're familiar with. So the first step here is essentially we generate a grid. Nothing too special here. It's just a 1D grid. Here is just a definition for the analytic solution. You can see it, right? No. Again, nothing too special. Now here's where the interesting part is. So we actually instantiate a solver, a very special solver, which basically solves for the scalar transport equation, right? We're only interested in convection, so this guy is basically true, meaning that we're not considering diffusion, right? We specify the wind velocity. Here, it's an overkill. We're specifying the Riemann solver. It's a 1D scalar. It's an overkill. We're just doing upwinding here. but we included it just in case someone wants to do, like for Jan was investigating for a bit, some multi-dimensional upwinding. You can do that there. But yeah, so then in the configuration, we specify the finite element method. So far we have, for this case, I guess, for the solver DG and standard DG and HDG. The finite element method order, the polynomial order describing the elements. So what we're interested in is, of course, the transient solver. So that's where it's transient, the time scheme that you prefer. The time interval, so starting from t0, which is 0 to 12, and the time step, delta t essentially, right? Here there's just like, if you're using an HDG formulation, of course it would make more sense. It would actually only make sense if you're actually doing static condensation. For a DG, of course, it doesn't make sense. And if you have installed it from source, you should be able to do real compile. Otherwise, like right now, you probably can't, right? And for this particular example, everything is periodic, so we don't have to do anything in terms of boundaries. You see it right here, right? And so all of this, up until this point, we haven't really allocated memory, we haven't done anything. This is where the part where Jan was talking about previously. When we do cfg.initialize, this is where we're basically allocating everything. So up until this point, nothing was happening. Right now, everything becomes expensive. And here we're just taking the actual solution, which we define it like this. This is how we actually provide you with a solution. You can, if you're interested in different fields, you can define different fields. And this is the analytic solution. And here we're basically the usual loop where we just run things in time and then see what happens. So this is, if you're wondering what this is a 1D mesh just for visualization. And if you run this, what you see here, remember we're just plotting the analytic solution and the numerical one. The analytic one is the orange one, I think, yeah. And this one is the blue one is the numerical one. Here it's this separate because it's an implicit order, whatever. But this is the ideal. If you scroll down a little bit, this is nothing more than an actual decorator. So what it essentially does is allows you to do some specialized routines just for testing, because at the end of the day, this is why we're interested in doing this, is just as a first step for testing to ensure, like, okay, you claim you have a spatial order of accuracy of 5, do you actually get it? You claim you have a temporal accuracy of 3, do you actually get it? And why not? So this is the first stage, and of course the interesting part is going into the compressible Euler equations and compressible Navier-Stokes equations on different problems, of course. So these are specialized routines. If you run them, I don't know, did we run them here? Yeah, I think so, yeah. So long story short, because this is really simple, here what we're plotting is the L2 difference between the analytic and the numerical solution for different temporal schemes. Everything is the same. These are the only things that are different. And as you would expect, everything goes down as the order of accuracy and time goes up. At some point, everything essentially becomes, everything becomes dominated by the spatial resolution, because this is not a very fine grid. And this is just the final time step of how the wave looks like. Nothing fancy. And I think this is pretty much about the simple wave equation. How do you, okay. I guess now we go to the 2D convection diffusion. It's a little bit more interesting. Again, these are simple problems. How do you do that? Okay. It's like inverted, it's weird. This is our beautiful Gaussian Hill problem. It's a 2D problem. Again, convection diffusion, still linear, so nothing exciting is happening, but it's supposed to be that way. It's just a model equation. The wind velocity or the convective velocity is essentially spatially varying. We can do that. And everything else is pretty much set up based on this configuration. This is the reference if you're interested. Now what we're interested in here is, I think everything is pretty much the same. The mesh is 2D, of course, that's different, but we also need far field boundary conditions. So this is not periodic. For this particular case on this grid, we can just pretty much assume that the far field conditions are 0. To be pedantic, you would probably have to prescribe the analytic solution. We already have it. But that's, I mean, details. So here we're just creating our grid. Nothing fancy, just a 2D square. This is where we actually generated, set the number of threads. Nothing so far very interesting. Here's the analytics solution, again defined based on the reference. You can look it up. And this is where the interesting part where we actually interact with Dream. Now we have a different solver, right? It's still a transport solver, scalar solver, but now we actually do need the viscosity, or like the diffusion term. So we set this to false, and the convection velocity is now, again, if you remember from the initial condition or the PD itself, it's minus yx. So these are coefficient functions, viscosity coefficient, all the usual stuff. And everything else is pretty much the same. Here the time goes from pi by 2 to 5 pi by 2, again, by definition. And here what we are also going to impose is, again, because this is a far field boundary condition, is 0 on the boundary. So this is why you have this guy here. And again, so far we haven't allocated anything. Here is where things here's where things actually get expensive. So now here we allocated everything that we need in order to start the simulation, and then we run it. And then what you're seeing here is just based on, I think, the implicit Euler. This is the last time step. This is literally like Gaussian but rotated. So by the way, the velocity, the wind velocity essentially is just rotating everything and diffusing. So nothing too exciting. And this is another decorator if you're interested at some point to, for instance, prototyping or doing something different. The idea is you have a specialized routines. You can set up something different and much better. I'm not like an expert when it comes to Python. And you can run it. And I believe we have something here. Okay. So also the usual thing here, I don't like to just present figures, but at least describing what we're seeing. So the first figure here is essentially you're looking at the deviation between the numerical variance and the exact variance. It's dominated by the implicit Euler, I guess, because it's too diffusive, so it's not much of an interesting graph for now. But for the bottom graph, you're seeing the L2 difference between the exact and numerical solution for different time schemes. Again, at some point here, basically you're dominated by the spatial accuracy. That's why there's not much difference. And I think this should be, should I start the Riemann stuff?
I'll do the compressible.
Okay. All right. So
thank you, Edmund. So again, the scalar transport, I know it's not interesting. The idea, interesting. So you said that. It's you said that. We mainly used it because the idea is you've seen all these implicit Euler BDF2 schemes that we implement them once and we can reuse it then for the compressible one. Such that for the we have a scalar, nice linear equation. We know there it works, and so we can extend it to the compressible equations. Now to the interesting part. Yes. This is where we started. So this is the compressible equations without any modifications. So we have our there you go. We have our continuity equation, which is, so we have our conservative variables u, which consists of a density of the momentum and the energy. And so the first equation is the continuity equation, the first is the conservation of momentum, and the third is the conservation of energy. We have the F, which are our convective fluxes, and the G, which are usually the viscous fluxes, where we have the deviatoric stress tensor and the heat flux vector. Especially for acoustic simulations, or where we actually started off is by neglecting the viscous flux tensor, because that's where actually the acoustics is incorporated. So it's in the Euler equations, just short, just to give you a short heads up about the equations. I talked before that there are, again, various configurations. I presented you now the compressible equations in a dimensionless form. In literature, when you compare again, you have different benchmarks. We weren't aware of that, but there are many different scalings to use if you have in a dimensionless form. We support that, so especially especially if you're interested in air acoustics, there are in acoustics there are two different scalings you use to get to the dimensionless form, and I think everything is documented here how we derive them, so you can actually pretty follow through. We have the reference quantities, and yeah, we have the derivation. We support different, for the moment, only one equation of state, which is the ideal gas law. Again, with derivations such that it should be kind of straightforward for everybody to understand. And with the, again, with the documentation. Keep in mind that everything that I'm showing you here is directly in the source code. So you code in NGSolve and the documentation in the same line, which I find very convenient. So everything is local. Again, so we also have support. So for the viscosity, for the moment, we only have the Newtonian constitutive relation and the Sutherland law. I don't know if you're familiar with it. The Sutherland law is if the dynamic viscosity of the gas changes with the temperature, with the current temperature. All of these we support for the moment, and I'll let you do the Riemann solver, and then I think we will already head up to the first tutorial and see if you can run, if you can install the Dream package.
Okay, so I should probably start by saying sorry, because this is going to be a very short one. The Riemann problem is something that is very rich, and that's something almost all the hyperbolic community knows about and is very familiar with. Not so much the elliptic community, but so the idea is, in a nutshell, we have a discontinuity somewhere. And this is, again, coming from a hyperbolic point of view. We have a discontinuity somewhere, so of course in the case of a DG, you can imagine two elements right next to each other. We need to do something right on the common face. You have, I guess I can use this. You have a solution on the left and you have the solution on the right. The way that we do that, in a nutshell, is essentially we look at the characteristics. So we do an eigendecomposition with respect to the actual boundary, and we look at the eigenvalues. The eigenvalues tell a small story. Essentially, each characteristic is traveling by a certain speed and in a certain direction. For our case, for the Euler equations, Navier-Stokes equations as well, of course, you can think of it as you have a spectrum of different characteristics, each traveling with the lowest one would be u minus c. Here u basically denotes the velocity in the normal direction. C is your speed of sound, the local one. And at the highest or the fastest traveling wave, it's u plus a. So this is interesting because technically if you are supersonic, which means your velocity u is higher than c, that means depending on if it's an inlet or an outlet, which for an internal phase depends on from which element you're actually looking from based on the normal, either everything would be a function of the left state or the right state. However, the interesting part is when the flow is subsonic, because when the flow is subsonic, you would have you have to deal with this, what they tend to call as a star region. The star region essentially says you have incoming data, you have outgoing data. So whatever is happening here is a combination of both. And in order to resolve it, you can of course do an exact method, which is basically the Godunov method, but that's very expensive. No one that I know actually uses it. The idea is we do an approximate Riemann solver. And approximate Riemann solver is a big topic. There's a book by Toro, basically the book. It's basically 1,000 pages, and there's a lot of different literature out there to try to do that. So essentially what I'm gonna do is say, this is how we're going to do that generically in a DG framework and in an HDG framework, and then call it a day. So let's start with the DG one, because this is essentially similar, if not exactly the same, as a finite volume. So if you come from that community, everything would be pretty much easy. Generically speaking, what you have is, again, a discontinuity. When you integrate by parts your PDE, you end up with some kind of flux on the surface. And it has to be a unique one, because the equations that Jan introduced are conservative by construction. So we need to preserve that structure. So that flux needs to be unique. So it has to adhere by some properties. Long story short, you can think of it as a flux that is a combination of the left state and the right state. I call them I and J here, the same stuff. The idea is there's some kind of central differencing, right? And some kind of dissipation, which basically is a function of a jump between the left and right state. And of course, weighted by some kind of dissipation factor, to call it simply. In this case, what you're seeing is basically a Lax-Friedrich. So what you're doing here is taking the fastest traveling eigenvalue and using this in order to say, like, I'm going to dissipate with respect by this factor. This is very diffusive. There's other stuff. There's the rho numerical solver and other stuff, flux vector splitting. It can become really complicated. But the idea is you're interested in a numerical flux, an actual unique valued numerical flux, and this is how you actually tend to do it in a DG framework. Now in an HDG, it's interesting, because this is where we have our facet variables U hat. So instead of defining the flux right from the get-go, what we do is we solve for a U hat, which is the facet variable, but we make sure that the U hat essentially ensures local conservation by saying that the jump of whatever flux we define, which is going to be a function of this U hat, which is this, by the way. So it's a function of the local solution U and the U hat, which is uniquely defined. It's supposed to ensure that the jump at a certain phase, an internal phase in this case, is 0. So this is how you get the local conservation. You get your U hat from here, and then you replace it here, and then somehow stabilization works out. It's interesting. But this is how we basically deal with the HGG version of a numerical flux, essentially. Oh, one more thing two more things I should probably say. So for a standard DG, we have to redefine the entire flux. For an HGG, we kind of all agreed that this is a good universal expression. All what we have to do is essentially define the stabilization tau to get our favorite equivalent Riemann solver, equivalent with respect to like the DG community, finite volume community, etc. Some examples that we currently have are for the HDG, which again, as a reminder, all we have to do is modify this guy. We have upwind, we have Lax-Friedrich, we have rows, we have a bunch of different stuff. I don't think it's actually important to actually go through them right now, but this is their definition.
You have the definition here if you're interested in, and you have also the references, because we're all already coming to the first tutorial, right?
This one points to you.
Yes, this one.
All right, so
thank you for the Riemann solver. So we're already coming to the first tutorial. I'm shortly introducing the weak formulation we're using. So I showed you the equations before. If you do integration by parts in an HGG sense, I mean, we have the time derivative that for the moment we're still semi-discretizing with a method of lines using the different time schemes that we provide. And for the fluxes, we do integration by parts, and then we have for the internal elements, we have this formulation, and here on the boundary, we have the numerical fluxes that Edmund just presented you. And again, for the facet, so this is for the internal test functions, and for the facet test functions, we impose that the jump of the numerical flux should be 0, and at the boundary we do some special stuff that we will talk about later, or we'll see later in the. So we have a boundary operator, which, dependent on which boundary operator we impose different boundary conditions, obviously. Which boundary conditions we can impose, we will see in the second tutorial, and we will also show you what we have developed or in the last years. Yeah, so you said the first tutorial, because Edmund introduced to you the Riemann solvers, is going to be a flow around an inviscid cylinder.
Can you shortly comment on where to find these files?
Yes, sure. So if you, I mean, we will have, what time is it actually? How much?
2 to 3.
Okay. If you manage to download it, clone the Git repo, you should, and you switch to the NGS Usermeeting 25 branch, you will find the tutorials in a folder. If you don't have, if you didn't manage to switch to the branch, we have it in the docs.
Yeah, there is on the homepage of the Usermeeting. There is on the right side the program, and there you have this link to this Google Docs, and there is again a link to the folder for session 3, I think.
Yes. So let me see.
Yes. So the last point is alternatively download the files from blah blah blah. Yeah, you should. Oh yeah, Jan is destroying my laptop in the meantime.
What the hell?
Wait.
It's one click, but not too deep.
No, actually, this should be too deep because he doesn't.
What the hell? Jesus Christ. Okay. Okay, can everybody see it? So, the first tutorial, I'm just gonna quickly skim through the tutorial. So this is an example from two colleagues from Huerta from Spain, which we've been collaborating with. It's just the entropy production around the cylinder in an inviscid flow. Inviscid means that we neglect the viscous fluxes, and by definition we are dealing with an isentropic system. So our numerical solution, the entropy, should, in the best case, if the numerical solution is good, remain constant. We're gonna test the different Riemann solvers, and then we will draw some conclusions that may also already be very clear to some, and others maybe not. We added to-do comments to give you a hint where you should change something, such that it's not too overwhelming at first to start using Dream. Again, I'm gonna skim through like Edmund did. So from Dream.compressable, from our favorite module, we import the compressible flow solver, we import the initial condition, far field, and inviscid wall boundary conditions. We have the usual NGSolve stuff, and here already we have a to-do for you, because we already did a lot of benchmarks with this ring geometry and mesh. So in dream.mesh you will find some predefined meshes where you can play around with the parameters and create a mesh. If you don't want to do this, I told you here, you can also do it with the OCC geometry, it's not a problem. Here we come to the configuration of the solver. So we're interested in a stationary solution. We will use a pseudo time stepping routine, which is implemented. We will use a conservative method and the HGG, which I just showed you, that discrete variation of formulation. We will, for timing reasons, or a polynomial order 2. And we use an implicit Euler because we're interested in the stationary solution, so we want it to be as dissipative as possible during the pseudo time stepping. The Mach number is set to 0.3. Again, here's the to-do. You can play around. The equation of state, we have the ideal gas with a heat capacity of 1.4. The dynamic viscosity, again, I said we're kicking out the viscous part, so it's inviscid. And we're using an aerodynamic scaling. The nonlinear solver is already set, so you don't have to do anything there. And I think, yes. And I also, why doesn't it show here? Okay. Here, since I want you to create a ring, we also want you to curve the mesh. And as an option, you can unset the curvature and try to observe what happens. We set the boundary conditions. So we get these far field fields. These are dimensionless quantities that are defined at the far field, so you don't have to explicitly know them. We give you a function to do that. The only thing you have to specify is the wind direction. So in this case, we're choosing 1 and 0, so in x direction, the wind purely blows in the x direction. We impose on the cylinder, we impose an inviscid wall boundary condition, which basically is a no penetration boundary condition, if you're familiar in CFD. And on the right and left boundary, we impose a far field, which for Euler equation means that we look, which basically is like an upwinding for the scalar convection. You look at the eigenvalues of the Euler system, and you distinguish between what is an outgoing wave and what is an incoming wave, more or less like the picture Edmund showed you in the Riemann solver. For the details, you can look up in the documentation. And we set the initial condition. Then we have this fancy wrapper because afterwards I want you to set. I give you an example how this would run. I have my decorator and I have my function where I want to test my Lax-Friedrich Riemann solver. The only thing I'm doing in this function, I'm config Riemann solver equals Lax-Friedrich. And I want you then to do the same thing and run the simulation, but just choosing a different Riemann solver. Yes.
So maybe we give 5 minutes to catch up and try around.
Yes, we give also 10 minutes maybe for the installation if there are some problems, because I heard there is no problem with Windows.
Okay.
Let's see.
I have an initial question.
Yeah.
So I think typically we have in CFD you often have the problem with time step size and mesh size.
Yes.
Do you have some automation there to control that, and how and what do you do?
So at the moment for the simulation I did, we didn't, because since we have HTG, we went full implicit. So the time step size was, let's say, not that a problem. But no, otherwise we don't have routines that are implemented if you want to go explicit.
You mean time adaptation?
time and space in like mesh size?
No, that's not.
I think this is like for like, this looks to be easily used engineer-wise. And I think like mesh size and time step size is usually the most critical error that people.
So the long-term goal would be probably to use some kind of a splitting method as well. With some question marks about that.
The idea, so that what you're saying is like the transient routine I showed you. This is a very standard routine where you just let it run. You can extend that.
Yeah, of course, you can make an adaptive PDF or whatever, yes.
Exactly. But just we didn't have the time currently to
Yeah.
do.
No, but this was the question, like,
Yeah.
it's on the plan or?
No, for the moment not.
Then, on what can this EOS depend? Like the viscosity model. I think there's a viscosity model. Right?
There's a viscosity module, yes.
Can it depend on arbitrary, like, I don't know, can you have some shear stress dependent viscosity, for example, or something like that?
For the gas compressible equations, I'm not sure there exists such a model, but in principle, yes. So on Friday, when we do the incompressible one, if we have time, I would like to do a non-Newtonian fluid as well. The only thing that, it's, again, then we have non-linearities and we have to look, but it can be, in principle, it's very modifiable.
And also like thermal also
What you want.
And couple it with the thermal solver.
Yes. It's just a connection, but you have a lot of freedoms. We can talk afterwards because there's something I didn't tell, which actually is pretty nice. That, or I can't. All the configuration you set have as a reference the top configuration. So you can go circular around everywhere and access everything, which is without circular imports, which is pretty nice if I need something from finite element, but I'm in the equation of state. It's kind of nice. What? Yes, we let. No.
It seems to be that there is troubles installing
bekommt das Input, aber was kriegt die jetzt Input? Die kriegt ein U.
Genau, ein großes U. Das große U ist dann.
Das ist auch schon eine Map, ein Dictionary.
Ja, aber kann ich da eben auch vom Druck ableiten?
Ja.
Aber wo kriege ich Druck?
In dem großen U. Das ist ein Dictionary, da gibt es dann zum Beispiel der.
Also U sind alle Flowfields, die das
Genau,
haben, oder?
genau.
Okay,
Und da steht dann zum Beispiel.
Aber wie macht ihr das? Sind da die Trial Functions oder die Build Functions? Was du willst.
Was du willst.
Genau, so weiter, das heißt, vielleicht manchmal Material selber definieren, nicht den Außenziel darüber rennen, dass wir dann die Divisionen erreichen haben.
Ja, das sollte in diesen Flow-Fields drin sein.
Okay. Ah, okay, das sind ein Haufen Worte. Ja, aber die Worte ist, woher weiß er, ob er jetzt doch die Grid Function, also den alten Wert oder den neuen Wert von dem haben?
Du meinst was?
Wenn du es in einer Lücken reinschmeißt, kannst du ja.
Was extra implicit machen?
Ja, genau. Da wäre.
Ja, ich habe das gemacht. Der ist nämlich der ist in dem Teil, der ist natürlich in dem Teil drin, der normalen Implizitkeit und das heißt, der wird. Genau.
Das habe ich mal.
Aber das ist das.
Für Viskose nehme ich mal den Einfilter her, weil ich habe mal Material gesetzt.
Aber du kannst ja quasi bei dem Erstellen der Viskosität kannst ja quasi eine Grid Function reinsetzen.
Ja.
Dann ist automatisch irgendwie der alte Wert.
Okay.
Dann merkt man, dass das keine Trial Function ist und dann sieht man es.
Aber das kann ich dann nicht in der Equation of State definieren, sondern das
Warum eine Equation of State?
wenn ich sage, okay, mein Viskose-Gesetz ist sozusagen die alte Grid Function.
Das ist die Viskosität, ja. Die
Ja,
Equation of State ist ja dann.
Aber ich kann ja sagen, meine Viskosität hängt nur von der alten Grid Function ab und nicht von der neuen.
Von einer neuen Zeitschrift einfach.
Alles gut. Kannst du
Genau.
auch mit einer Apply eventuell auch machen, oder? Du nimmst das raus, die Viskosität, gibst dann beim Apply die Build Function ein. Also du kannst alles mit Try und Test Functions machen. Und die Graphen und hast dann das Apply ein.
Ja, aber die Idee war ja jetzt, ich nehme schon euer ganzes Factor her, aber ich implementiere eine neue Viskosität. Und aber ich will, weil ich weiß, dass da irgendwie keine Ahnung, aber nur für die Person, das ganz brausig ist, würde ich sagen, okay, den Teil nehmen wir explizit, nehmen wir Viskose, die hängen nicht vom alten.
Ich glaube, jetzt gerade auf der Welt geht es nicht, oder?
Dann brauche ich, sonst muss ich das ganze Server-Frame.
Aber das ist eine Kleinigkeit. Im Endeffekt ist das nur in der Viskosität.
Das ist eine Kleinigkeit, aber man muss
Ja, aber ich war nur ein Input, das so sagen, das ist aber interessant. Dass man sich sowas definieren kann halt.
das ist gut zu wissen, sorry.
Weiß nicht, ich finde das für mich so das approachable, weil sonst ist nicht so
Am schlimmsten war dieses Skalierungsding dazu. Das Skalierungsding zu verstehen. Der Weg lang es sollte alles übersetzt sein, aber dann geht es ja in die Standard. Die sind halt immer so, was Von mir aus auch die
da ist die haben schon 201, das von der
Aber das ist ja
Download
dann
und
hast du
das
ja irgendwelche graphischen Abhängigkeiten.
Die Schwierigkeit ist wahrscheinlich, wenn du sagst, du willst das explizit, du musst
Gute Frage.
Also immer den perfekten besten Soll, was ich aussucht, das ist
Ja, ja. Post-Processing oder wie sagt man, zurückrechnen. Aber das ist ein Kopf. Das ist ein Kopf. Das schreibe ich mir auf.
Okay. I'm sorry that so many of you are, or I guess at least I saw some, cannot install it. What?
What was the issue? You know what was the issue?
No, with Windows, I know that.
But what is the issue with Windows? No Git maybe?
No Git doesn't find the module. I mean, even
Okay, but that's a path problem, then maybe we have to fix this in.
No, but I thought that if you have the virtual environment, everything is.
Did you install it with -e? Or
It was in the code. It was in the.
it did copy paste.
Okay.
But maybe
Yeah, maybe
continue now.
We'll fix it. I think we'll fix it later. So, I mean, this was, yeah, just let's say first hands-on example. So I told you we already have some predefined meshes. What I wanted you, like, we have this cylinder row mesh, which Philip already did, which is kind of nice. So this is our mesh that we used for the simulation. Was
Yeah, this was, yeah, it's handmade.
handmade, yeah. Yeah, you can look at the code in the and well, I forgot to say what we're actually plotting. Sorry about that. So again, like Edmond said, we initialize our solver. We get our solution fields, and then we get the specific entropy of our discrete solution, and we get the far field entropy, which should be constant, right? And we show you the relative error, so the discrete divided by the constant entropy -1. And just because it can be negative and positive, so I'm just plotting the absolute value of. The first example was the Lex Friedrich. I think Edmund mentioned it. You know that the Lex Friedrich is it's very robust but very dissipative. And we see around the cylinder how like the changes so we get some entropy errors around the cylinder. The same is for the HLL, so it almost looks the same. It's a little bit better in the background, but it's still very let's say entropy violating compared to the better ones, the HLM. LEM, the ROS solver, and the upwind one. The last three have just for you to know, they're obviously more computationally more expensive. If you play around with the polynomial order, you will see that. You will see that the entropy violation obviously decreases. But if you play around with the curvature of the mesh, you will see that for higher polynomial order it will not converge, while because of the curvature they write in the paper. I cannot tell you exactly why, so sorry about that, but in the paper they state that the curvature representation is very important to get this example right. It's 3, so we continue with the examples. One example I really like now is the work with. I really like because we did it, but also because again of dream features. Is it? This is the solution. Sorry, I don't know. So is this moving vortex in an inviscid flow? So this is quite a crucial, or when I started doing my PhD, I thought it's an easy example, and now I'm still stuck with this example. It's actually full compressible, again Euler, so no viscous effects, and it's an inviscid vortex. I'm gonna show you the contours such that you can imagine it. Or let's do it now. That took a while.
Yes.
So I'm showing you the velocity currently and the vectors. Let's see, too big. Can you see it? Can I change the color of the... Well, you see it's a vortex. It's
I want to use the function color.
Tick on the surface.
Surface,
You
yes.
don't see the surface at
okay.
all.
Okay. Yeah. So you see, I'm showing you the velocity of the initial velocity profile minus the u infinity. So I'm subtracting the base flow. So you see it's rotating, but the whole vortex is moving from here over this boundary. So the idea of this example is to let you implement different boundary conditions. So you will have, which was our topic for the first year. So we have different boundary conditions that you can impose on this boundary, and based on the boundary condition, you will see less and more reflections being generated at this boundary condition. Which is kind of that's why I said it really this example triggered me for a long time, because I can already spoiler it. There is no optimal solution, or I didn't find an optimal solution for now. If somebody has one, please come forward.
Could you shortly explain what's the issue, what's happening, and why we get a reflection?
So the physically is because as soon as the vortex, assume that the vortex is right at the boundary, we don't know what's the vertical structures behind the boundary. So, and it's pretty hard because the vortex in this moment is in equilibrium, right? So again, like the example before, we have Euler equations, so it's isentropic, it's in equilibrium, and as soon as it goes over the boundary, you disturb this equilibrium. So you cannot represent the vortex anymore correctly, and everything that you cannot represent correctly anymore will get reflected back. That's the short answer. We can set different boundary conditions, they have the different impact, and I will show, I already...
So basically you can also think of, so you have this vortex structure, and in order to keep the vortex structure you must have a low pressure in the middle of the vortex, right?
Yes, to keep it in equilibrium.
Exactly, and then as soon as you're moving through the boundary, suddenly you don't have this compensating flow back, and then you have this low pressure in the middle, which somehow has to fall apart, and it will produce a pressure wave at the boundary.
Yes.
So
that's the, I gave you here again, sorry, just to be precise, this is a problem in subsonic flow. In supersonic flow, because Edmund told you, this is not a problem at all. But since we're interested in air acoustics, this can become quite tricky, because we need information traveling from downstream, upstream, and that's when it becomes tricky. I gave you some to-dos. I already imported one boundary condition I gave you a hint then below which boundary conditions would you like to try. And the nice thing that we're gonna now also implement, add to our routine are these input-output sensors. So we in Dream we already have defined various sensors that if you would like to measure the pressure difference or the L2 pressure difference over time, we have sensors that do that for you and capture after each iteration. Capture you this pressure difference in the L2 norm or just some norm, or we have point sensors that you can place around. We'll see that in the next example. I want you to add one, and I'll go follow through again. So we have again our setting. Now we have an aerodynamic scaling. No, we had it also before, sorry. We have a different Riemann solver now, a fixed one. We have the upwind, we have a BDF2, and we have now a transient simulation. Before we had a pseudo time stepping. I am activating here some input-output streams. That's no concern to you. What I would like to emphasize is this guy here. So again, I'm getting my far field, my dimensionless far fields, and I'm initializing this exact solution. I mean, these are the equation I showed you before. And the crucial point is, or the interesting part is now here. So I set our time to transient, and I'm accessing now the time t. Where we're using a NGSolve parameter, which we can update accordingly. We know that the exact solution is traveling. It's like a scalar convection equation. So we know that the exact solution travels with the base flow after each time step. So we can access this t, and we now get a time-dependent exact solution, which is represented, which is this UE. We add it to the initial solution because we know the t is 0 at that point. So when we initialize the initial solution, the vortex is right in the middle. But that's when I'm getting back to the sensors. I want you here now to add from Dream.io this domain L2 sensor. It's a sensor that does the integral over the whole domain of these fields that I already predefined for you. So it's the L2 norm of the exact solution minus the discrete solution of the density, of the pressure, and of the velocity. I want you to add these fields to the sensor and add the sensor to the configuration. Since we already defined the exact solution to be time dependent, the sensor will automatically detect that the exact solution, when we solve everything, the exact solution follows the correct time step, like the, yeah. Again here then, objective of this example was to set the boundary condition. I predefined for you a, just let me run this. I predefined for you one example. So if we run this, we see this vortex. I'm showing the pressure now. This vortex moves, reaches the boundary, and we see now how this pressure waves get reflected back into the domain in a kind of, what do you say, EPS wave? Yeah, like EPS. Yes, I defined for you here some boundary condition I would you like to try out, and also predefined already some plotting where you can see which boundary condition works better and which is worse. So we have, yeah, it's already, time is flying, so.
Yeah, I think we do 5 minutes this trial out, and then the last few minutes you just
the last
show
few
the example.
Yeah. Yes.
Yeah. nicht mehr groß auf die.
Also
du kannst einfach sagen, was da steht. Also nur, dass das für Non-Reflecting Boundary Condition steht. Das kannst steht, da kannst du auch drüber fahren, ja, genau. Und dann sagst du ganz kurz, ja, das soll jetzt. Wann das jetzt mal Reset gemacht, dass es auf Misch kommt, dass das heißt.
Da gehe ich jetzt einfach drüber und sage, schau, aber das wird lang dauern. Es ist ein Tutorials.
Ja, du machst noch kurz, ich glaube, du warst schon ziemlich am Anfang.
Ja.
Ich sage einfach nur kurz, was das Ding ist. Das ist das Ding von dem Beispiel von Anfang. Das ist das C. Spoiler ist schon viel.
Yes, I'm just going to show that, I guess. Time is, I'm gonna quickly skim through the solution, a possible solution. So this is the sensor we added to the solution, is keeping track of the L2 norm while I'm solving everything. I have the far field boundary condition I showed you. I'm adding this outflow boundary condition. The outflow shortly just imposes acidic pressure, which maybe you know acts as a Dirichlet boundary for acoustic waves. So the pressure is basically constant and everything gets reflected back. And then we have this characteristic boundary conditions, which is currently in a preprint, which we developed, which adds some, let's say, shortly tangential terms to better capture this vortex moving out of this outflow boundary. And if you added the sensor correctly, this is the L2 norm I'm showing. So we have the far field boundary condition. This is the first one I showed you, where you have this alternating pattern, which over time has a big reflection back into the domain. Then we have this outflow boundary condition, where again you have more reflections into the domain. And then you have our boundary condition, or that we developed, that produces, I would say, significantly less reflections than the other one. Yeah, why are we doing this? The last tutorial, there's no time for it, I guess, because we can skip it. But all we did now was an inviscid flow. We obviously want to have a viscous flow. So the example Philip showed you in the beginning is a viscous flow around a cylinder. We know that there are vortices shedding, and these shedding produces acoustic waves, which we saw. I wanted to give you this example. It's unfortunately, it runs a little bit longer. You can eventually do it during the coffee break. We gave you also the solution. I'm just gonna, if you do follow the correct steps, I already added you some added you some post-processing, because there's some post-processing needed. But if you do it correctly, you should be able to see these acoustic waves being generated from the shedding of the vortices. Keep in mind, it's a very let's say big mesh, because of timing reasons. The simulation we did took, I think, 3-4 days for the picture that you showed. And if you place then we can have a look at the lift coefficient. We can have a look at the drag coefficient, and all of this you can do it with some sensors implemented. If you would like to try it, we can discuss it during coffee break. But I think it was long enough, so let's wrap it up. And yeah, I hope you like it. I hope we get some feedback, some what you would like to have, what you would improve, and let us know. And yeah. Thank you for your attention.
Okay, so we have now a coffee break for half an hour. The coffee should be ready already, and a lot of food. So please eat some sweets. Somebody has made a mistake in the ordering, apparently.
There's a cake for the whole.
Okay, and at 4 we will start with our next talk, a short talk, and then we will have a poster session. And I will have a short comment at the end of the break before the talks, but we will come to that. All right.
Okay, so let's continue. So it's a pleasure to welcome Lukas Kobia. So Lukas is of the same generation, grew into NGSolve since a young student, together with Christopher, Matthias, Philip. First generation from Vienna. Lucas has done a lot of, Lucas already likes solving large problems, and he's responsible for a lot of the MPI parallelization in NGSolve. You know, if you do MPIs, the tricky part is how to get your things solved. Doing the assembling, operator application is all easy, but getting it doing good preconditioners in parallels is Lucas' task, and he's very good at this. And then it happens that Siemens had an opening in the company, and unfortunately they also thought that Lucas is very good and they put him. So, but happily Lucas is some part hobbymäßig working for Siemens, but also still working for NGSolve and maintaining his add-on package, a parallel AMG solver, NGSolve, and that's what.
Yes, and doing that I'm trying to strike a nice balance between introducing new bugs and reintroducing old ones and then fixing them all the night before the user meeting. Okay, so I want to give a rough overview of what's in this package, and kind of want to focus in the end about some of the reusable building blocks which I needed to implement, which may be useful in a wider context than strictly AMG methods. So there are basically 3 solvers in this package. There's one for H1 problems, one for elasticity problems, and then there's a relatively new development with big quotes on the relatively. It's an AMG method that's monolithic for stocks, so it actually solves the momentum equation and the incompressibility constraint. And I want to go through those 3 relatively quickly, and then, as I said, focus a little more on the smoothers. One quick note on installation. So this has, from the start, been the primary target has been Linux with MPI. You should be able to make this work without MPI, and even on macOS. If you're on Windows, good luck. So if you want to try this out, it's a relatively painless CMake install nowadays, and I also implemented this pip install at some point, but I'm not 100% sure it still works. Does on my system, but that doesn't always mean much. But just ask me and I will be happy to help you if you're interested. Okay, so the next thing, I had some technical issues with this laptop and with my workstation where I'm actually having the Jupyter notebooks run. So I implemented 2 versions, one is parallel and one is serial. And I'm gonna pick and choose between them because in the serial the visualization is sometimes a little messed up. And then in these notebooks you will see a bunch of commands that come from seemingly nowhere, and it's just these 2 Python files which I will make available with the rest of the Jupyter notebooks. They just contain some utility commands for assembling some stuff or running a solver in a loop and measuring the time, which is not the focus of what we're talking about. Okay, so let's go for the okay, good. So some of you may have seen that before. When you want to do something with MPI, with parallel in Jupyter, you spin up this cluster, and then you add this cell magic in front of every cell you want, not the Python process that's running with Jupyter, but this cluster in the background to execute. So that's just something you have to see. And it works, I guess. Okay, so H1, yeah, that's the other thing that just works. If you're doing AMG, H1 is pretty simple. It's not, that just works. It fits very well to the H1 discretization, and since it fits well to the discretization, it's not so difficult to build a solver for it. So you can use this, but these AMG methods for H1 are a dime a dozen. So if you use this, if you, for example, use the NGSolve PETSI interface, you're gonna get something that's very similar in performance, very similar setup and solve time. And there's not much of a value proposition of going for this custom AMG when you have PETSI available just with a few pip installs. The the story is a little different, but not too different for elasticity. That's also something that's kind of the next step up in AMG methods. If you have an AMG method that works for H1, you can usually find some modifications to make them kind of work for elasticity. And the method that's implemented here kind of belongs to that. It's a relatively standard smooth aggregation method, so it's quite similar to what's implemented in PETSI. So if we set up oh, yeah, okay, there's no pictures now. Hold on, let me restart it in serial such that we can see some pictures, because that's always okay. Cluster is spun up at some point.
Does it increase the font size a bit?
Yes. Or no, I don't know. How do I do that?
Just control and
oh, yeah, alright, okay.
Oh, yeah.
Okay. Oh, it probably, yeah. Yeah, it probably didn't like that I spun up 2 clusters. Okay. Okay, yeah, there we go. So we set up this, this elast 3D or 2D from the NGS AMG package, and we do the preconditioner test and solve CG for this beam, and then we draw it. And now the picture doesn't show up. Okay, that's not a big deal. That's exactly why I implemented 2 versions of these. Oh, okay, I think I see. The problem is not even... Okay, I will just see if that's gonna do something eventually. So this is just a standard beam 1 times 1 times 10, and it's clamped on one side, and then there's some load applied. And it was able to solve this. And the story is very similar here. For this type of problem, you're...
Maybe it's the Jupyter problem.
Yeah, the other problem is also that the Jupyter cluster is actually, or the server is actually running on my workstation, and I'm just connected via an SSH tunnel, so all kinds of factors involved. But in general, you can expect to get also relatively similar performance out of PETSI and this library for that kind of problem. Okay, so that executed. All right. And it didn't draw anything. I love it. Okay. So I just wanted to run through this quick. What I wanted to say was this is also pretty much a standard problem. So in any situation where you're gonna run into trouble with these Boomer AMG or PETSI AMG libraries, this is maybe has some features here and there which you can try and play around with and sometimes get it to work, but it's not a silver bullet. So I wouldn't expect that this is now gonna work. Oh, there we go. So I think it's the Wi-Fi connection actually. Okay, yeah, and there we go. So PETSI also had no trouble solving this. And so this is now running and doing something. All right, so what I was showing here is going to take forever. Yeah, but because I was drawing it again and now it should be faster.
The measures
Yeah.
are showing, so they're showing
Okay.
200K unknowns per second per
Yeah,
Or?
yeah, something like that. So you're gonna get that for simple problems on like 1 or 2 or 3 ranks until you hit the memory bandwidth, and then it's gonna go down on single node. And multi-node is gonna take an immediate hit because you have the communications between the nodes. But yeah, for these simple types of problem, that's about what you can expect. Another trick to pump this number up is only to solve to 1e minus 4 or something. Okay, so good, here we have it. So what I wanted to show here is an example where this can break down much faster than you would think is, what if we just take this beam and we make it longer and longer? So we are running it with length 1, 5, 10, 20, 50 up to 1000, and we get the condition number we get out of PETSI and out of the NGSolve, and we draw that. And that's pretty much horrible. So you can tinker around with the settings, and you can do a limited number of levels and all of that stuff, and I'm sure you can get better out of PETSI than this.
I wanted to say it's better than PETSI.
Sorry?
Yeah,
I mean, this looks better, but honestly, if neither one is really usable, which one is better? Okay, so in this NGS library, I spent a little time on kind of harder problems, and I implemented some experimental mitigation strategies. So you can, for example, change the smoother to block Gauss-Seidel, and you can use this improve its option, which is going to try and iteratively improve the prolongation matrices without blowing up the graph. So that's something you can try. It's not fully parallelized, so your mileage may vary. But for this, it works pretty well. So it starts to break down at some point, but it works okay. So, and this often also works if you're doing relatively thin meshes, as long as in the thin direction you still have a couple of elements and you don't have 2 stretched elements. For stretched elements, I have something that's even less stable than this, so I'm not even gonna show it. Okay, so that's a lot of time spent on this, and so let's look at the Stokes AMG, and I'm gonna switch to the serial notebook here because I have some nice pictures to show you, and that's definitely not going to work if the other one didn't. Okay, so in contrast to what I showed before, this is a very non-standard AMG method. There's one out there which I found that's kind of similar. It's out of Lawrence Livermore. It's called PARELAC, and I have a link here. But I think what I have here is much simpler coarsening. So I'm not up to date with what happened with PARELAC in the last 2.5 or 3 years. But if you look at the paper, from there they have a list of like 8 conditions or so they need for their coarsening to give a coarse graph that has again all the properties they needed from the fine graph. And the coarsening here, because it's much simpler and just trimmed to HDiff type methods, yeah, I think it's much easier and probably much cheaper. And I have a pretty fast smoother and some tricks to keep everything, to minimize the amount of communication you have to do in parallel. Basically, if you set up your coarsening with a couple extra rules, then you can keep all of your Galerkin products local, and you have to do minimal exchanges in the smoothers, and you don't run into this problem with which they often do with especially the classical AMG, where your coarse levels get not only denser but also denser in the sense of cross-partition communication. So if you have an HDiff heritage or an MCS formulation with an HDiff velocity and tangential facet traces, you should be able to plop this into this Stokes AMG and solve Stokes or Brinkmann or something. Yeah, and I put a paper here from Luke Olsen and Nathan Bell from like 2008 where they did the coarsening, I think, even smarter. So this is not going to tell you much, but this is just setting up HDiff heritage. The fine details here don't matter. And then we throw this into Stokes HDiff grad 2D or 3D, which are these preconditioners. again, there are a ton of options to tune this. This option here, if it's set to P1, it's basically the deluxe version. It's going to try and maintain all of the P1 functions in all course levels. And as a smoother, we're going to use a Hipmeyer smoother, which I'm going to explain in a second. And this is this fast block smoother, which we are also going to come to. So let's see if this drew something, because this picture is really nice, because I stole the geometry from Philip last year. Okay, yeah, so this is this Tesla valve. It's two-dimensional, but the solve took only 1.2 seconds. So you're solving over, looks like 300,000 degrees of freedom per second, and core, where it's just one core, but it's a Stokes problem, not a Laplacian. Okay, good. So how does this actually work? So the principle is to mimic this geometric multigrid you have for HDiff, which you can do, where you have a series of L2-like spaces, which for the AMG we are only not actually constructing, but we pretend we constructed, and you have a series of HDiff-like spaces that are also nested, such that the divergence of the HDiff spaces is exactly the L2-like spaces. And you have a series of H1 or H-curl-like potential spaces, which you're also not explicitly building, because you're only really interested in them as the divergence-free subset, so as loops basically, because, and I will show a picture for that too. And then you have this discrete curl or orthogonal gradient operators from the potential space into your HDiff space, and you have the divergence from your HDiff space into the L2 space. And the L2 and HDiff prolongations and differential operators commute. So if you construct all of that such that it works, then you can set up the dual, you take your mesh, you set up the dual graph. So your elements become vertices, your facets become edges, and your edges in 3D or vertices in 2D become loops, because we're not interested in actually constructing an H-curve, we just need the loops for this smoother that's robust in the divergence constraint. And we coarsen that graph, which is going to introduce an agglomeration of elements, and that's going to induce a agglomeration of faces and then an agglomeration of edges, which is a little more difficult with the coarsening of these loops, but you can look that up in the Luke Olsen paper. And then you do, on every one of these element agglomerates, you do local harmonic extensions, and you solve a small Stokes problem, and that gives you your coarse basis functions, and you're pretty much good. Okay, so let's go back to a smaller, simpler problem, and let's look at some basis functions. Okay, so what we have here, this ladder moves the levels. So if we go to level 0, and we turn off, we look at the elements themselves, and we, so how was this turn off surface? Oh, that's nice, I didn't know that existed. Okay, so these are your HDiff functions, right? And then you go up 2 levels. That's the Wi-Fi connection, it takes a while. So, and these, maybe look at a later one. Yeah. Okay. Maybe level 1 is better, because there are actual like made up degrees of freedom on outside the domain here. So okay, this is a good example. So you're looking here at the divergence of one of these coarse basis functions. So it's a HDiff-like function that goes from one agglomerate here in red to the other one. So you have a positive divergence on the one side and a negative one on the other, and it's constant. And so, yeah, okay, I thought so. And this is how it looks. And in addition to this equivalent to the lowest order HDiff functions, it also maintains a couple of P0 or P1 traces. And yeah, the only thing is the tangential traces are mixed in with the normal ones. So you don't have this clean separation of normal and tangential degrees of freedom you have on the finest level. And the other thing are these loops, and you need those for the potential space smoother. So you need an explicit representation of the divergence-free space on every level. And so let's go, yeah, level 2 is fine. Let's look. So, yeah, this is, so I need to find one that's only within the domain, because as you can see, this loop here, for example, it's for the coarse thing from this vertex. It goes from the outside, inside, and then outside again. So that's why it doesn't look so good. But if we go to level 1, there should be a couple loops that are completely in the inside. Yeah, this one. No, this one not. Oh, yeah, this one, for example. Okay. Turn off the surface and. Okay, and yeah. Yeah, so, and these are basically the potential space. And you use those for potential space smoothers that are robust in the divergence constraint.
So these are now like vertex patches where you have loops on vertex patches?
Yeah, something like that. And in 3D it's loops around edges.
Yeah.
So what's simple if you build the AMG for HDiff and not HCurl is that you don't actually need explicit basis functions for HCurl, and if you want HCurl you also need H1 because you need a potential space for that. And here it's relatively simple. You just need the HDiff space and then these loops, and that's not that difficult to do. Okay, good. So the last thing I wanted to show, because this is a component which I think can really be reused pretty well, are the smoothers that are here. Because NGSolve does have smoothers, but they are not MPI parallel, or rather they are MPI parallel, but only additively. And what I implemented here, they are multiplicative. So, and they also hide communication behind local computation. So they spin up one thread that's constantly hitting the MPI library in order to cumulate the vectors, or while the main thread continues to smooth in the interior. And you can use those directly from the NGS AMG package, and they're basically a drop-in for the NGSolve Gauss-Seidel and block Gauss-Seidel smoothers. So as an example, if you wanted to use it as a preconditioner, so you use one forward, one backward iteration of the smoother as a preconditioner, then you would do this here with an NGSolve smoother, and it looks very similar with the NGS AMG smoother. There are just optional additional parameters you can give it in a residual, and it can keep the residual up to date, which is sometimes useful if you want to do multiple iterations. You can save some computations with that. But let's see. So performance-wise, there's both for the normal regular Gauss-Seidel and the block Gauss-Seidel, there's usually not a huge difference in serial. Yeah, so this is, oh, it's done, okay. No, it's the first one is done. So this test smoother is just running the smoother in a loop for like 50 times or so, and then it's reporting the time. Okay, so here it's 0.09 and 0.09 for NGSolve and NGS AMG Gauss-Seidel. So that's what you can expect. The difference is that this stuff in NGS AMG actually works in parallel. And I can show you that in a second. Let's just let the block Gauss-Seidel one, yeah. Okay. Good. The thing I implemented for this Stokes AMG is a dynamic block Gauss-Seidel. So when you have a high order matrix, especially for HDiff, you have a very repetitive non-zero pattern. And if you can write your linear algebra such that you exploit that fact, you can save a lot of bandwidth and you get quite a lot of better performance out of it. So let's test the SPMV first. So we convert this HDiff matrix we set up above into a dynamic block matrix, and we just run SPMV in a loop. So instead of 0.1 seconds, it's 0.036. So this is a special case because the HDiff is really fast because it has extremely repetitive sparsity pattern. But if you're running lots of high order stuff, you can probably get some benefit out of this. And the second part of this equation is the smoother build on this. So you can, of course, also exploit this in the smoother. And actually this dynamic block smoother creates a dynamic block matrix, and then it smooths on that. So not much there. And there you're again getting almost, you're getting here actually more than a factor of 2. Which I found pretty nice because this isn't that much code actually. Okay, let's just one moment and look at this in parallel. Because why am I going on about the multiplicative smoothers? The nice thing about multiplicative smoothers is that you don't need a dampening parameter and you're basically guaranteed that it converges eventually. So always takes a little time to spin up the... Okay, good, then skip this one. And with this parallel, and you see here that even in parallel, it's all eigenvalues smaller than 1, which for the smoother means it's convergent. So that's very, very useful in practice often. And yeah, there's also a Lawrence Livermore paper about these hybrid smoothers, how you can do it such that you're always convergent even in parallel, where you can't be truly multiplicative. But yeah, that's all I had.
Thank you very much, Lucas. Questions?
About the last condition number, so the one eigenvalue is less than 1, slightly less than 1, and does the other one go to 0?
Yes, because it's not robust in H.
Ah, okay.
It's like Jacobi, but the upper eigenvalue is always smaller than 1.
Okay.
It's only the smooth side.
Yeah.
To be combined is a question.
Right. This is a component of a solver.
Okay.
You could also use that type of technique with geometric multigrid, but maybe for geometric you could do something matrix-free, which would be even faster.
Didn't mention it, but how large problems have you solved with this package?
Okay, so with the Stokes, the largest one was like on 60 cores, 50 million or so. But with this newest version, whatever I can fit on my personal computer, because yeah, and the elasticity I ran on 15,000 cores or something like that. I'm not going to say it performed perfectly, but it ran.
And how many unknowns on this 50,000?
Yeah, it was a billion or 1.5 or something.
It scales pretty well.
Yeah, if you have a problem where this smoothed aggregation approach works. If not, then yeah, you have other problems before you can worry about scalability.
But similar problems as all packages have.
Yeah. Yeah. Okay. Then thank you.
Thank you. Okay, now we are done with presentations here. There should be hanging some posters around in the back room. Yes. Okay, so people with posters are now presenting the posters. We are going over there. Short presentation, and then later time to talk with the people having the posters. other people's. And for not starving, only looking at the posters, there will be also some food coming in later, the drinks and food. The drinks and also food is coming. But the food we don't have a funding, but here we have some crowdfunding suggestions. So if whenever you should put in 10 euro or something like this, and the food will be done with this.
Okay.
Okay, something more today?
No, we will follow now Christoph basically because he will show us the details.